Alright, I'm going to explain conservation of energy and charge as it relates to Kirchhoff's laws. So I'm using the gravity and water analogy, and I'll explain later why that won't work exactly, but for now it's good enough of an analogy. So the outside regions here are pumps that obviously pump water up to increase its potential energy. And we're saying that this energy that the pump gets in order to pump the water up is coming from the universe. That's just a technical term that we use in physics. Everything that isn't the system is the universe. So the system is everything that's in front of you right now. And the pump is getting energy from the universe. The system stores the energy as potential. Then it releases the energy as kinetic energy first. That's the current picks up some kinetic energy, but we allow for all of the kinetic energy that's picked up to be dissipated in these water wheel resistors. So it's really a constant current going through a bunch of little water wheels acting as one big resistor. So anything that's picked up from the universe is given back to the universe as heat. That's conservation of energy. And it doesn't matter what path you take, as long as you start from one location and end at the same location, then you've picked up potential and you've given that same amount of potential back. That's simple enough. Conservation of charge is saying that any amount of current that flows in any of these regions can't build up in any one of these regions. It can't store any more than is allowed to flow. So if something's flowing here, something's flowing here, then that same amount, these two added together, must flow out. So whatever's in goes out, obviously. Otherwise you're building up. It's conservation of charge. Now you got to be careful with which way you're assuming the currents and the potentials are going. And I'll demonstrate that now. If you notice this center point here, the center is the lowest potential of the storage areas, but with the exact same sources and let's say the exact same resistor values. Actually, it can't be the exact same resistor values. The center resistance, this guy here, must have changed because now the potential from here down to ground is different. So this resistance here has increased. So it makes it more difficult to send a current down here. So this potential stays higher. So you can see automatically you can't assume that you know which way the currents are going, because here the current's going down towards the center, and this other one, it's not going down towards the center. It's the exact same configuration of the circuit, but now the current is going this way, away from the center. And as a consequence, you can see that this current has to be modeled as going down the pump instead of up. So now the pump is actually working in reverse. To maintain the potential at this location, it has to accept current going into it. But as I just showed, we don't know which way the currents are going yet until we solve the circuit. So let's take a look at this schematic and label the currents arbitrarily for now, and then solve every parameter in the circuit in order to find out which directions the currents are actually going. So doing a voltage loop starting here, which I'm just calling my common location. I haven't labeled it. I could call any location my common, but it makes the most sense to do this one. because it has the most branches coming into it, and it's also the easiest to relate to the sources. So if I start here and I go up Vs, and then I'm calling this V1, I'm calling this V2, I'm calling this V3. So if I go up Vs, and then I go across R1, if I follow my polarities, I'm going down V1, so I'm minus V1. And then this is just a label, Vn. We'll talk about this in a minute. Then I go down V3, minus V3, and that gets me back to 0 here. And I know that the sum of all voltages in a loop, the sum of all voltages is equal to 0. And then taking this other loop, I have, going up to here, I have 2Vs minus V2 minus V3 gets me to 0. So this is this guy. And then I've done a Kirchhoff's current law right here, summed all the currents at that node. So I have I1 and I2 going into the node equals I3 going out of the node. And just putting everything on the same side of the equation, I have this guy. Okay, so now I have 3 equations and 3 unknowns. 3 equations, 3 unknowns. That means I'm pretty much done. I just have to do algebra now to solve for the 3 unknowns, because I have 3 equations and 3 unknowns. My 3 unknowns are the 3 currents, because Vs is known, all the resistors are known, and all the V1 and V2 and V3 are written as, using Ohm's law, they're just written in terms of the currents. So if you take a look at I1 here, in relation to this, the voltage here at this node here, by the way, voltages are always the energy at one location with respect to another. And a node voltage is always the voltage at some location with respect to ground. That's the definition of a node voltage. So you know automatically, since this was labeled Vn, it's the voltage here with respect to here. It's not the voltage here with respect to here. That's V2. That's actually minus V2, if you want to be technical about it. And the voltage from here with respect to here is minus V1. Because V1 is the voltage here with respect to here. V2 is the voltage here with respect to here. You always start with the positive. So Vn is the voltage here with respect to ground. That's how you state a node voltage. So I1, in terms of the voltage here and here, we already know what I1 is with respect to V1, but now we know what V1 is because we know the voltage here and we know the voltage here with respect to ground. So we're going to write I1 equals V1 over R1, and we know what V1 is. If you just look at this, V1 is the voltage here minus the voltage here. So we have Vs minus Vn over R1. So this gives you enough to find when I1 is positive or negative. Depends on the size of Vn with respect to Vs. But what is Vn? So looking up here, Vn is the voltage from here to ground, which also happens to be V3, because V3 is the voltage across this resistor, and this resistor is from here to ground.